Welcome to this training program on steel bar quality. My name is Pat Wannell and I'm Chairman of the Industry Technical Committee of the Cold Finish Steel Bar Institute. Quality is of vital importance to all of us. The more suppliers, producers and users speak the same language, the more we are going to achieve together. So the Technical Committee has put together this special program to help all of us better understand the quality attributes of our product. The program is divided into a series of modules. In Module 1, we will introduce you to the important concept of quality attributes and then go on to describe internal quality, which is the foundation of all product quality. Throughout the series, you will meet members of the Technical Committee, and they will draw on their particular areas of expertise to help explain important concepts to you. May I wish you good luck with our program.
Quality. What is this thing, quality, that everyone seems to talk about? That we all try so hard to achieve? Where does it come from? And how is it created? What does it look like? How is it measured? And how can it be protected? The quality of a material is the characteristic that defines its fitness for a particular use. This quality characteristic consists of attributes, physical or functional states that can be measured. Desirable attributes, those that help a product do its job, are called benefits. Undesirable attributes, attributes that would harm a product's performance, are known as defects. The attributes of steel can vary widely in a number of areas. This great range of characteristics is one reason for the tremendous number of steel grades in use today. Some combinations of attributes can be achieved at the same time in one material. Other combinations are mutually opposed. The more there is of one attribute, the less there must be of another. The positive and negative quality characteristics of these steel grades must be carefully balanced when choosing a steel for a particular purpose.
When we're studying steel bar quality characteristics, we find that they can be divided into 5 major groups, the so-called building blocks of quality. These building blocks can be imagined to function synergistically as layers in a quality pyramid. These layers would be internal quality, those qualities which are set by the hot mill suppliers, surface quality, which is set somewhat by the hot mill suppliers as well as the cold finishing, properties, which pertain to not only the mechanical properties such as machinability and hardness, but also the strength and ductility, dimensional quality, which is very important with the cold finishers because the dimensional tolerances on a cold finish bar are, for example, 10 times tighter than those of hot rolled bars. And last but not least, presentation. The presentation pertains to preserving those qualities by packaging and presenting them in such a way that, for example, the bars do not get nicked or get rusty. This module will pertain to internal quality.
Internal quality is the basis for all the other steel bar qualities, and nothing influences internal quality more than the basic production processes in the hot mill. The production processes for making the hot-rolled bars used in cold finishing include basic steel making, where iron is turned into steel, secondary treatment of the molten steel to adjust chemistry, temperature and physical uniformity, casting of the molten steel into solid form and its subsequent cooling, and hot rolling practices, which change the size, shape, and internal structure of the still hot steel forms. Many variations are possible in these 4 steps, allowing steel makers to produce steel with combinations of characteristics tailored for specific purposes. Even the seemingly simple choice of heating methods used to make the basic steel has significant consequences. The basic oxygen furnace, or BOF, takes molten iron that's fresh from the smelter and injects pure oxygen at high velocity to create virgin steel, steel that has never before existed. It takes a great deal of energy to produce this new steel, which has relatively low levels of nitrogen and other residual elements. The electric arc furnace, the EAF, saves an immense amount of energy by starting with existing scrap steel. This reprocessed steel has a chemistry based on carefully selecting the scrap used in the mix. The carbon and silicon levels are similar to those in BOF steels, but nitrogen and residual element levels are usually higher. The potential energy savings of electric furnace steel must be balanced against BOF steel's relative freedom from excessive levels of nitrogen and tramp elements.
Now, there is a way around it in electric furnace steels, and that would be to use more expensive scrap, which is lower in residual elements. But there are also other ways to trim and to control the chemistry of the steel, and that is with the use of secondary treatments. Now, these are treatments while the steel is still liquid, just after the steel has been made and is still in the ladle. Now, these are not mandatory, but these are optional treatments that can be done to the steel, and they are listed as follows. You can trim the chemistry of the steel, and you can bring it into the ordered range by adding certain amounts of little additions of certain elements. You can also use either induction stirring or electromagnetic stirring, and the purpose of this is to distribute the bath composition more evenly within the ladle. The third thing you can do is control the slag, and by controlling the slag, you can be doing things such as skimming the excessive slag, and by doing that, it would promote a cleaner steel. You can also degas the steel by pulling a vacuum on the steel, and what that does is it pulls out the dissolved gases prior to solidifying, and these reduction of these gases will also result in a cleaner steel. And the last thing you can do is control the temperature with electric arc heating. And the purpose of this is to put the steel at the correct temperature and at the correct time when you're just ready to cast it, so it's most optimum for solidifying. There are 2 processes used to solidify steel into shapes that are used for further processing. Those are ingot casting and continuous casting.
In ingot casting, molten steel is teamed from a ladle into a series of cast iron molds that are open at one end. The steel can be top poured into the open upper end, or filled from the bottom with the method called bottom poured. These 2 methods can influence the internal quality of the same batch of steel in different ways. Even the shape of the mold can influence internal quality. A mold may have its big end up or its narrow end up. These are also known respectively as big end up and big end down molds.
Now, each shape has its own advantages and a cost associated with it. The big end up molds, the steel is poured in from the top, filled in here, and the main advantage of big end up molds is that as the steel is poured in here, the steel will start to effervesce and give bubbles. And what will happen is, as these bubbles start to form and they'll start to float up, they actually float away from the surface of the ingot mold, as you can see. Contrast that with big end down ingot molds, and when you get bubbles that start to form and float up, the bubbles can actually become trapped at or near the surface of the big end down ingot molds. Well, you say, well, good grief, then why don't we just get the big end up and be done with it? Well, it turns out that there are other costs associated with these two things. A big end down ingot, or the product of a big end down ingot, is actually lower cost. And the reason for that is that when, after the steel has been solidified, it's easier to strip the solidified steel out of a big end down ingot than it is from a big end up ingot mold. Now, at first it doesn't sound right, because how would you get the steel out? But what they do is the big end down ingot mold is actually a two-piece mold. The bottom of the ingot is called a stool. And what they will do is they'll cast the steel and allow the steel to solidify. And once the steel has solidified, they can actually grab the top of the mold itself with a crane and actually just strip the mold right off the top. Contrast that with a big end up mold. To get the steel out of it, they have to turn the mold on its side and knock it out from the bottom. So there is a less cost associated with getting the steel out of a big end down mold. Also, something that contributes to a lower cost of a big end down mold is that they normally have to, after filling the steel up, they have to discard a certain amount of the steel that is unusable for hot rolled bars. If you just look at it, because there's a smaller area up at the top of a big end down mold, there is obviously less volume of steel that would have to be thrown away and recycled, as opposed to taking a big end up mold. But again, you have to weigh the advantages. This is lower cost, and it has more yield from a steelmaking standpoint, but you do have a problem, or a potential problem, of little air bubbles floating up and getting entrapped near the surface of the solidified steel. Again, here, with the big end up, it is a little bit more expensive to cast this way because there's less yield in the product, and it is more difficult to strip. But from a surface standpoint, a big end up mold renders steel that has a generally better surface quality.
Continuous, or strand casting, the other major method of solidifying steel, uses a completely different mold than ingot casting. The mold itself is copper, not cast iron, and it's cooled with water sprays, not air-cooled. Both ends are open so that solidified steel can be drawn out the bottom as molten steel is poured in the top. A movable dummy bar plugs the bottom of the mold to contain the molten steel at the start of the casting sequence. The molten steel is released from a ladle into an intermediate container called a tundish, then into the mold. Control valves, called gates, in the ladle and tundish allow the levels of molten metal to be held constant in the tundish and mold. And because the mold continuously empties as it's being filled from the tundish, one strand cast mold can do the job of many ingot molds.
The advantage of continuous casting is that you can have one essentially long strand of steel that comes out, and the yield, or the product yield of the steel coming out, it's very uniform, and you don't have to discard nearly as much steel as you would if you were doing ingot casting. Now, I've drawn two shapes here, and there are two basic shapes to casting in continuous casting. You can have either a square or a rectangular mold, or you can have a circular mold. And the basic difference between the two pertains to how the steel solidifies. There is an optional process called electromagnetic stirring, where you can actually stir the steel, the liquid steel, within the mold before it solidifies. That can be done with a rectangular mold or a square mold. With a round mold, you can actually spin the mold to accomplish the same effect. And the basic effect of either spinning the mold or using a process called electromagnetic stirring serves to homogenize the structure of the steel as it's solidifying. By comparison with ingot cast steel, strand cast is much more uniform from the beginning of a heat through to the end of a heat. On an ingot cast steel, which is basically a batch process where the steel solidifies in the actual ingot mold, there are phenomena that happen in the ingot that, for example, the top of the ingot is different in properties than the middle of the ingot, and which is different from the bottom of the ingot. It's a solidification type of phenomenon. But in strand casting, because all of the steel that you're pouring through is basically liquid on the inside, and you're pouring the steel through it, all of the steel sees the same method of solidification, and that turns into more uniformity, again, from the beginning to the end of a heat. And besides the uniformity, the strand casting process, either be it with the square or rectangular versus rotational circular molds, strand casting allows you to improve the yield of the steel, and because as you're pouring all of the steel through, all you have to do is just discard the very end of the cast one time. Again, comparing that with ingot steel, each ingot you would have to throw off the very tops of the product. So there is a yield saving with strand cast steel.
The final step in the production of hot-rolled bars is the hot rolling process. As steel cools, it typically forms extremely large grains that make it unusable for bars. Hot rolling, squeezing and reforming the steel above certain temperatures, can reduce these grain sizes to suitable dimensions, and in addition, aids in dispersing non-metallic elements more evenly through the iron structure, called the matrix. The greater the reduction ratio, the original cross-section area compared to the final cross-section area, the more efficient and effective this process becomes. So, though it takes more energy to reheat and roll larger beginning ingot or strand cast sizes, these provide greater final hot reduction ratios for a given final bar size. Following hot rolling, bars will often undergo various tests for surface quality. Internal quality characteristics can be placed in 4 groups of related items: chemistry, structural integrity, microstructure, and inclusions are categories which define certain types of quality characteristics related to internal steel bar quality. The chemistry of a steel is the particular mixture of chemicals that makes up that batch or heat of steel. The way a steel will perform in service is influenced more by its chemistry than by any other internal quality attribute. This is because chemistry plays a major role in determining the final state of the other internal qualities. Many chemical elements are employed to create specific effects in steel. The way they act in the steel and modify the effects of other elements is complex, but there is some basic information that is useful when evaluating a steel's fitness for a specific purpose.
Steel used to produce cold finish bars are generally produced in 2 broad categories: carbon steels and alloy steels. By far, most of the steel sold in the U.S. are carbon steels. And the main alloying elements for carbon steels are naturally carbon and manganese. Now, the other elements, such as nickel, chromium, molybdenum, which are part of a chemical composition, in carbon steels, these elements are generally referred to as residual elements. Carbon and manganese are the primary elements in carbon steels. Now, people who do machining will also specify a minimum content of sulfur, and they may specify also lead or bismuth as a machinability additive. One more important element in carbon steels involves the choice of silicon. Now, certain grades of steel are ordered specifically without silicon, and these steels are generally called coarse-grained steels in the carbon steel family. And the presence of silicon with other elements are called killed steels, and when you have aluminum or vanadium or columbium in there, these steels are also called fine-grained steels. Now, again, with carbon steels, you have a choice of using killed steel versus non-killed. And basically, the choice of killing a steel or not involves trade-offs. The presence of killed steel will generally improve the surface quality of the steel. That is because there are elements that kill the steel that will actually gobble up air bubbles or carbon dioxide bubbles in the steel as it's solidifying. However, the presence of these elements can also be detrimental to machinability. So again, for people who machine steels, namely in the free machining steels, these people would not buy aluminum, vanadium, columbium in their steel, and they generally do not specify silicon in the steel. Another broad category of coarse-grained steels would be the 1144 steels, 1141s. These have sulfur in them for purposes of machinability. They are carbon steels, and depending on the desired level of surface quality, a grade like 1141 or 1144 steel can be ordered with or without specific amounts of silicon in them. Now let's contrast carbon steels with alloy steels. Again, alloy steels have as one of the basic elements in there is carbon, but generally the alloy steels have combinations of either nickel, chromium, or molybdenum. And I'll just use the chemical symbols for them: nickel, chrome, or moly as it's called in the trade. Now, what distinguishes these from the carbon steels is that someone would purchase specific editions of these three elements, and the reason someone would buy these in an alloy steel is that there is a desired response to heat treatment. Now, these elements are expensive, and if you can get away without using them, if you need, for example, only to machine the steel, or you do not need a specific strength level that is achievable with heat treating, you can get away without these. But there are customers who do need to use, have a response to heat treatment, and they will specify levels of nickel, chromium, and molybdenum in their alloy steels. Now, the cold finish steel bar industry handbook has a description of all of the different elements that go into steel, as does your workbook. And again, some of the other elements that would be besides carbon would be manganese, phosphorus, sulfur, silicon, nickel, chromium, molybdenum, and then some of the grain refiners, which would be aluminum, vanadium, columbium, which is also known as niobium, titanium, and various other elements. Again, they are in your cold finish steel bar handbook. The other two types of steel, which we'll not really get into, involve tool steels and stainless steels. But because cold finish steel bars generally have no implications with these groups of steel, we'll say no more than just to mention them here.
The exact amounts of alloying elements are calculated to produce specific attributes. To ensure that the final levels of these elements are within the required ranges, chemical analyses are made of samples from both the molten steel, called a ladle analysis, and from the solid hot mill form at the bloom, billet, and hot-rolled bar stages, known as a product analysis. The results are provided by the hot mill supplier in a report to its customer. These report values can be critical to the selection of the proper steel, especially when the level of an alloying element is being held to a very low level, as it often is in microalloyed steels.
There's another class of steel which is in between the carbon and alloy steels, and these are called microalloyed steels. These are sometimes also called HSLA steels, which stands for high strength, low alloy steel. Microalloyed steels are characterized by increased strength and good ductility while still in the hot-rolled condition, as opposed to cold drawing. And the strength of microalloyed steels is gotten by putting in nitrogen in the steel in combination with vanadium, columbium, or titanium. And another group of elements that can also be placed into microalloyed steels are what are called needles of nickel, chromium, or molybdenum, sometimes copper and zirconium also. But the amounts that is put in these elements is nowhere near that amount for alloy steels. Again, it's just to increase the strength of the steel in the hot roll condition. Now, a microalloy can be made with either the same tensile strength or yield strength as that of cold finished steel bars, but cannot do them at the same time. And basically, tensile strength refers to the ultimate strength of the steel that you can pull on it before it begins to break, begins to neck before breaking. And yield strength refers to the amount of stress that the steel can take before it permanently deforms. Now, if you have the microalloy steel that has the same yield strength as a cold-run bar, it turns out that the tensile strength of the microalloy is more than a cold-run bar, and therefore its machinability is not quite as good as a cold-finished bar. Also, if you have a microalloyed bar that has the same tensile strength as a cold-run bar, it will have a lower yield strength. Another aspect of microalloyed bars is that they can be cold-drawn. And when you cold-draw a microalloyed bar, you can achieve strength levels that could not be gotten with cold-finished bars of the same grade alone. Now, all of the strengths and elements that we're talking about are all contingent upon the bars having a good internal structural integrity.
The category of internal qualities called structural integrity includes the attributes known as pipe, unsoundness, and segregation. There is probably no normal use for a bar with pipe. Pipe is an internal defect that begins in the casting process. As an ingot or continuous steel strand cools, a hollow area can form in the end. This hollow consists of oxidized and decarburized steel, scale, and occasionally non-metallic deposits. If this pocket of materials isn't completely removed in the shearing step known as cropping, it will be rolled into the finished bar as a central hole. These surfaces cannot be rolled together in the hot mill and will always remain a structurally weak area. Pipe that runs to the end of the bar can usually be spotted in a visual inspection. Secondary pipe, which is closed on both ends, can't be seen, but can be detected by ultrasonic inspection. Sound waves created at one end of the bar will be reflected by the internal walls of the secondary pipe and returned to the end of the bar to be detected and displayed on an oscilloscope screen. Unsoundness is an internal defect that may be caused by too high a casting temperature and too little hot working. Often called porosity or looseness, this defect occurs during solidification of a cast form, when dendrites, very long crystal grains of steel, grow inward from the already cool solid skin. As the steel form cools and contracts, the dendrites tend to contract more than the solid skin, leaving open areas between the grains near the center. Atmospheric oxygen never reaches these surfaces, so adequate hot working can re-weld them into a solid bar again. This defect can sometimes be detected by ultrasonic inspection. One other type of internal integrity characteristic is segregation. When steel solidifies, it tends to attract mostly iron atoms to the grain structures that form. This forces other elements to remain in the molten portion, concentrating them in the areas that solidify last. Slower cooling rates give non-metallic elements more time to migrate, resulting in areas that are much higher in a concentration of these elements, positive segregation, or lower, negative segregation. Temperature effects like convection currents and gas bubble formation provide many areas for segregation. Thus, killing a steel, that is, adding a chemical to absorb the gas bubbles, can often lower the levels of segregation. The detection of segregation involves a hot acid etching process to speed up the different rates of surface etching, followed by microscopic examination of the etched surface. Much can be discovered about the composition and structure of a steel by such microscopic viewing. The way steel is organized on this fine level is known as its microstructure. A steel's microstructure is strongly influenced by its chemistry and by the way it cools. At about 1330 degrees Fahrenheit and above, iron can dissolve nearly 2% of its weight in carbon. Below this point, it can hold only 0.02% of carbon by weight, only 1/100th as much as the hot phase. The final microstructure is determined by what happens to the rejected 99% of the carbon as the steel cools from its high-temperature austenite phase to its room temperature ferrite phase. The rate at which this cooling takes place is one of the major factors in this process.
3 different types of microstructures that can be obtained with the different cooling rates of the steel are pearlite, bainite, and martensite. Now, pearlite is generally the most desired microstructure for machinability. And it really deals with the steel cooling through 1330 at the slowest rate of the 3 for the different structures. If we jump for a second to martensite, the cooling rate for martensite is so fast that the carbon in the steel at high temperature does not have a chance to diffuse into the low temperature steel. In other words, the carbon gets kind of locked in as to where it was when it was at the high temperature form. So when you lock in the carbon, you create a very hard structure called martensite. Again, this structure is very desirable in terms of alloy steels when you want to heat treat for high strength, but it is absolutely no good for machinability. And then there is one more structure that kind of falls in between martensite and pearlite, and that is called bainite. And essentially, let's just call it an in-between microstructure, which is determined by a slightly faster cooling rate than forming pearlite, but not so fast as to form martensite.
Pearlite shows up as a series of alternating black and white lines, which are platelets of iron and iron sulfide seen on edge. If these structures are held near 1300 degrees Fahrenheit for an extended time, the platelets contract into rough spheres. This is known, therefore, as spheroidized grain structure. Bainite appears as a feathery iron carbide structure. Structures vary slightly in the 2 available types of martensite. The untempered martensite, straight from a quench bath, shows no obvious structure, no grain boundaries. Tempered martensite, which has been heated to just below its phase change temperature, has a structure resembling small needles, although there are still no details to define grain boundaries. These microstructural differences can often be used by metallurgists to determine the hot rolling and heat treating histories of steel samples. But if the structures are so very small, how can we see them to make such a determination?
Now, so far we've described the different types of microstructure, pearlite, bainite, and martensite, but we really haven't talked about how you can actually see these different microstructures. After all, they are very small. Now, the way it's done is with the aid of a metallurgical microscope, also called a metallograph. Now, we're not going to really describe exactly how a metallograph works, except to say that we look at a polished sample that has been prepared and polished to a mirror-like finish, and we have to actually eat away the surface of the steel with acid to reveal the structure of the steel. Now, what I'd like to draw for you is a surface of a steel bar. Let's say this is the inside of the structure here. And up here, this represents, for example, your eyeball looking down at the steel with the metallurgical microscope. Now, if you take a piece of steel and you haven't etched it in acid or anything to reveal the structure, as the microscope looks down at the surface, there's such a flat surface here that you can't see anything. All the light gets reflected back up, and this steel surface just looks plain and white. We don't see any structure. And what we have to do on this piece of steel to see what the structure is underneath. In fact, I'd like to just draw a few of the grains of steel underneath that happen to intersect the steel that we're looking at here. Bear with me just for a second. Now, what we do is we etch the steel with a very light solution of hydrochloric acid in methyl alcohol called nitrile. And what we do is we'll dip the surface of the steel in the acid, and the effect that it has is that it eats away the steel. And although it eats away the surface at one rate, it preferentially eats away the grain boundaries at a different rate than it does the rest of the surface. So what it does is it actually puts a little bit of relief into the surface of the steel. Now, you're asking, well, why is that important? Well, what this does, this relief that's put into the steel, now as the microscope or your eyeball looks downward, any area that is still flat gets the light reflected straight back up, and that area looks white. But what happens is when the light, as it scans across here, intersects an area where the grains are, it'll bounce off to some other angle, maybe coming down here and bouncing off here, and this light here does not get reflected straight back up into the microscope, and the areas where the grain boundaries are appear as dark lines. So you can actually see the structure of the steel on a polished sample that has been etched in acid.
Not only the shape, but the size of the steel grains is revealed under the microscope. It's actually possible to measure the grain size of high-temperature austenite with a procedure called the McQuaid N test. But grain size is typically measured in room temperature ferrite.
And it, too, is done with a metallurgical microscope. Typically, the magnification level that you use is 100 magnifications. And what you do is, as you're looking at these grains, you want to get an idea of, again, relative size of these. Now, the American Society for Testing and Materials, the ASTM, has a formula that will tell us whether the steel is so-called fine-grained or if it is coarse-grained. Now, to tell whether steel is fine-grained or coarse-grained, we scan the steel at 100x magnification, and we want to count the number of grains that would intersect a 1 square inch area. This I'm going to call 1 square inch. A 1 square inch area viewed at 100x magnification. And what you do is you count the number of grains that are in an average 1 square inch area viewed at 100x, and you count them. And you plug them into a formula, which is as follows. The number of grains is equal to this formula, 2 to the n minus 1. Now, what does that mean? This number n is the grain size that's reported, and we'll talk about that in a second. Let's just take an example. Let's say, for example, that you counted an average of 8 grains in a 1 square inch area viewed at 100x magnification. So if you had 8 grains here, that is equal to 2 to the something power. And that's 2 cubed, 2 to the 3rd power. Now, something minus 1 has to equal 3. So this would be 2 to the 4 minus 1, or 2 to the 3rd power. In this case, if you found an average of 8 grains in 1 square inch, the grain size number n would be 4. Now, if there were more grains, there would be 2 to a larger number, and then the grain size number would be a higher number. So what all this says is that if the grain size number n is between 1 and 4, this is considered a coarse-grained steel, because relatively few number of whole grains would fit into 1 square inch at 100x. There is a term called fine-grained steel, at which this number is 5 to sometimes 8, or generally it's called 5 and finer, that maybe you could have even 1,000 grains in 1 square inch viewed at 100x. So, just to repeat, when the grain size number is 5 or finer, and sometimes it's specified as 5 to 8, this is considered fine-grained steel. When the number is 1 to 4, then the grain size is considered coarse grain steel. Now, of course, when we're measuring grains, really we're not including the inclusions.
Inclusions are non-metallic particles in the steel grain matrix. These structures can come from chemicals added to alloy or deoxidize the steel, or from worn, high-temperature linings that insulate ladles and other steel-making tools. The larger examples can be seen with the unaided eye, but inclusions are normally detected and analyzed with the help of a metallograph or an electron microscope. Inclusions may be deliberately created by the addition of lead or sulfur to produce the free machining steels. All 4 groups of internal quality attributes are essentially created and fixed in the bar during the various hot mill production processes. Cold finishing will not normally correct internal hot mill defects, but close inspection can prevent most defective materials from being used as the raw material for cold finished products.